Greetings, my name is Vishal Ramnath, and I will be presenting paper 108 titled Quantification of Nanoparticle Diameter Uncertainties using Arithmetic and Harmonic Means from Kernel Density Estimate of Dynamic Light Scattering Data. So I'll give the context of the problem, I'll explain why it is an issue, what is being investigated, what is the approach to investigate it, and what are the results. So this is the abstract. So without going into too much detail, nanofluids are prone to temporal instability issues. The thermal conductivity and viscosity vary over time, and the stability is correlated to the values of the thermal conductivity and the viscosity, which are in turn correlated to metaparameters such as the nanoparticle diameter, the equilibrium temperature, and the volume fraction. I will go through the results. So experimental data indicates that the thermal conductivity drifts over time, typically over 24 hours, and the stability is in some way related to the thermal conductivity and the viscosity. This is some representative experimental data. So as we see on the left-hand side, the weight fraction will vary over time, typically over 1 or 2 dozen hours, and because the weight fraction varies over time, so too will the thermal conductivity. So to analyze the stability, it is useful to investigate how the effective thermal conductivity and the effective viscosity vary as a function of the nanoparticle diameter. However, there are different ways to work out the diameter and the corresponding uncertainty from the experimental data, typically with dynamic light scattering data. This is the general form or the formulation in mathematical terms. I won't go through the details. However, the general pattern is that with an increase in the volume fraction, typically the thermal conductivity will linearly increase while the viscosity will non-linearly increase. With an increase in temperature, typically the thermal conductivity will linearly increase. On the other hand, the viscosity will linearly decrease. And of course, with an increase in the zeta potential, the stability of the thermal conductivity and the viscosity will obviously increase. So this paper is basically to consistently work out the expected nanoparticle diameter and its uncertainty from the dynamic light scattering data. Why do we do this? Because the existing methods are ambiguous, unclear, and inconsistent. So if you have inconsistent nanoparticle diameter data, the nominal values and the uncertainty, you will of course have inconsistent and potentially misleading stability information. I won't go through the details. This is dynamic light scattering equipment, typically various laboratory equipment such as an Anton Paar DLS meter. And this is basically the way to post-process the data. Without going into too much details, you work out the autocorrelation function from a laser intensity, you do some statistical data, you work out the decay constants, and you infer the hydraulic diameter from the Einstein equation that relates the hydraulic diameter. So typically when you run a nanoparticle mixture through a DLS, you get the so-called particle size distribution, the PSD. However, the PSD is not exactly equivalent to the corresponding probability density function. You first have to poststress the particle size distribution to work out the PDF, the probability density function. I'll explain in detail how to do that a little bit later. So there are some combination of issues. The issues, as I mentioned, is that the PSD cannot be directly used to get the PDF. If we look at the previous result, we see that they have different shapes and different nominal values when you post-process the data. So an existing limitation is that typically only log-normal PDFs give explicit formulas, and then you get different results depending on how you work out the average. In other words, the arithmetic mean or the harmonic mean. And presently, there is no existing formula to work out the corresponding uncertainties. So this paper will investigate these results and give the results. This is the algorithm, which is explained in more detail in the paper. You essentially step through the curve, you read off the fractions, and you work out the corresponding discrete values, and you run the discrete values through a statistical library known as Seaborn, which is based on Python. These are the formulas. So you have a generalized formula for the average or the mean. G is a weighting function, and you have different weighting functions for the different arithmetic mean and the harmonic mean. These are the results at the end of the day in generalized terms. So at the present time, there's no generalized formula for the uncertainty of the harmonic. I derived it from a discrete point of view. When we run it through some typical representative data for different volume fractions from 0.5, 1 to 1.5, we get the results for the arithmetic mean and the harmonic mean. And when we visualize this graphically, we see that the arithmetic mean is inconsistent with the harmonic mean. And the inconsistency cannot be explained purely in terms of the error bars. That means they are inconsistent, and based on the theory and the results in the paper, the recommendation is to use the harmonic mean because it gives a better accuracy and is a recommendation according to the ISO standard for particles. So we see that there is a systematic error, and of course the harmonic has a smaller uncertainty. To wrap up the presentation, the harmonic mean and the arithmetic mean are demonstrated to be inconsistent, and the harmonic mean is recommended as it gives better quality results with a smaller uncertainty. This is the end of the presentation, and then there are of course a few references. Thank you very much for your time.